Welcome to an introduction to real analysis. We're going to go through section by section, continuing now with chapter 1, section 4, intervals and the size of the real numbers. What are we going to do? This is a pretty short section. There's really only two objectives. First, we're just going to formally introduce notation and definition for how we write intervals in the real numbers, which is probably nothing new to most students in this course. And we're also going to give a quick proof due to Cantor that the real numbers are an uncountable set, that they cannot be put in a bijective correspondence with the natural numbers. So let's get into the definition. I do want to remark this is possibly slightly non-standard. It won't be terribly objectionable, but we'll see what I mean in a moment. Suppose you have two real numbers a and b. We define intervals with square brackets on both sides, or a parenthesis on the left and a square on the right, or a parenthesis on the right and a square bracket on the left, or parenthesis on both sides, to be sets of real numbers that satisfy certain inequalities related to a and b. Wherever there is a square bracket, you have a non-strict inequality, but wherever there is a parenthesis involved, you include a strict inequality. So there's just sort of a bunch of combinations of square brackets and parentheses that might arise here. And everyone is probably thinking, of course, we all know this. Why am I calling this non-standard? Well, indeed, why? As long as a is less than b, everyone knows this notation. And we're going to call those proper intervals. When a is less than b, these are all totally defined very reasonably. It is, however, sometime convenient to ask what happens when a is equal to b. Now, in this case, you can see that this inequality, if a and b are the same number, there is a single number that satisfies both of these inequalities, a or b itself. They're the same number, it doesn't matter which one. Now, if a equals b, there are no solutions to these chains of inequalities, so you would have an empty set. This is what's slightly non-standard. We are going to find it pretty convenient to allow writing this as an interval, even if it only contains a single number. So the interval from a to a, as long as you have square brackets on both sides, is actually going to be an interval. We're just not calling it a proper one. Also, if a and b are in the extended reals, you can define the following. Note, we are never going to include a square bracket where there is a plus or minus infinity involved. It wouldn't really make a difference. If you ask for being less than or equal to infinity, that's the same as being less than infinity. Okay, so here, the interval from a to infinity would be all x's bigger than or equal to a, or just bigger than a, or less than or equal to b, or just less than b. And generally, we want our intervals to be subsets of the reals, not the extended reals. So note, even if we include a plus or minus infinity in the notation, we are not including plus or minus infinity in the set of values. The values have to be real numbers. And here we have proposition 1.4.1. It's worded slightly differently than in the text, although it is equivalent. A set I within the reals is a proper interval if and only if it contains two different points, and for any 2 points in the interval, the closed interval between those two values is a subset of I. Proof is omitted. It is an exercise in the text. So now on to the meat of this section, so to speak. The real numbers are not countable. Let's assume that they are. So the real numbers may be listed out, x1, x2, x3. Our assumption is every real number appears in this list. So any real number you might be able to find must be in this list. That is our assumption. Note, for any proper interval from a to b, we've actually proven that there must be both rational and irrational numbers inside that interval. Therefore, there are real numbers in that interval. Meaning, there are x sub i's that belong to that interval. Because remember, every real number is one of these x sub i's. So if you find a real number, it must be in the list. So the real numbers that are in between a and b are in the list. But by the well-ordering principle, if they have these indices, there is in fact a smallest index, x sub I, so that x sub I belongs to the interval from a to b. We're going to use this argument as part of an inductive construction in just a minute. By assuming the real numbers may be listed out, for any proper open interval, there is a first term in the sequence that belongs to it. Okay, so assume we've listed out the real numbers. Let's just define some a's and b's. A sub 1 is x sub 1, b sub 1 is x1 plus 1. The point here is just to make a nice open proper interval. b1 is bigger than a1. Also note that x1 is equal to a1, so it does not belong to this interval. Now we're going to make an inductive assumption. We're doing an inductive construction, so here's what we're going to assume we have done at every step. We've constructed a bunch of A's and B's, where the A's are getting bigger, the B's are getting smaller, but the A's are always smaller than the B's. Okay, we start off with just this being less than that. Let's assume we've constructed some A's going up and B's going down, but never actually crossing one another. Okay. By assumption, this right here forms a proper interval, which means there are real numbers in it. Every real number is in our list, so find the first index, x sub capital N, that belongs to this interval. Make that your next a sub k. So having picked a sub k minus 1 to b sub k minus 1, if I find something that's in this interval, it's definitely bigger than the previous a, so I keep this part of the inductive construction going. Then I simply pick the next b to be anything in between wherever that number was and the right endpoint. Between x sub n and bk minus 1 makes a new open interval containing real numbers, so there's a real number in there, pick that to be bk. Okay, and also observe, since we are making this x sub n our next a, it doesn't belong to the interval ak to bk. So having assumed the real numbers can be listed out, what we have done is we've constructed a bunch of open intervals, ai, bi. By picking terms from the sequence to be the a's and then some other real numbers to be the b's, where capital N is the first index for which some term of our listing out of the reals belongs to the previous interval we had. So x sub n for any index smaller than that capital N does not belong to this interval, because capital N was the first term that did belong in here, so all the previous ones do not. But now, because the A's are getting bigger and the B's are getting smaller, these intervals are what is called nested. One interval is always a subset of the one that came before it, nesting all the way back down. So, since these xn's didn't belong to this interval, they also don't belong to this one, or the previous one, or the previous one, and so forth. In other words, whatever the capital N is, which is the first index that lands in here, x sub little n, up to that point, doesn't belong to any of these intervals of smaller index. Also, we're picking a new x at every step. You can't reuse things here because our intervals are not including the endpoints. We're nesting down. So our first a1 was x1. a2, the smallest index it could possibly have would be x2. And then a3, the smallest index it could have would be x3. In other words, the smallest index you can pick is the index that you are now constructing with your A's and B's. So if you picked a certain term of the sequence to be a sub I, that index had to be at least as big as I. Combine that with the argument up here, every single x sub n doesn't belong to any of the AI's where the I is up to that index. Okay, so for example, x sub 10. Maybe you pick it as an A, maybe you don't, but it can't belong to A1 through A10. A1, B1 through A10, B10. Okay, so we've listed out all of our reals. We constructed sequences of A's and B's that achieved this. Note that every single xn does not belong to any of these proper intervals where the index ai to bi is smaller than or equal to the index on the x we picked. We've already done that. That was in the previous slides. So let's take all of the A's we picked and put them into a set, and all of the B's we picked and put them into a set. So every element of the set of A's is less than every element of the set of B. In other words, the set of A's is bounded above, and the set of B's is bounded below. Okay, every single A is a lower bound on capital B, and every single little b is an upper bound on the set capital A. So since every single A sub I is a lower bound, every single a sub I is less than or equal to the inf of B. So every single a sub I is less than or equal to the inf of B, but that just tells us the inf of B is in fact an upper bound on the set A, because every single a sub I is less than or equal to the real number inf B. Therefore, the sup of A, the least upper bound, is less than or equal to one particular upper bound that we found. But note, the supremum of A cannot belong to the set A, because remember, the set A is formed by these a sub i's that are always getting bigger. So if the sup of A was in the set A, the next index, A sub n plus 1, would be bigger than the sup of A, and therefore this wouldn't really be an upper bound, but it's the sup. So the sup of A can't belong to A. But the sup of A also can't belong to B. If the sup of A belonged to B, then the sup of A would be one of the B's. The next B would be even smaller. The sup of A is less than or equal to the inf of B. We've already argued that. So you would find a term in the B's less than the inf of B's, getting the same contradiction. So whatever the sup of A is, it's a real number that doesn't belong to the set capital A, and it also doesn't belong to the set capital B. So what do we have so far? The sup of A is a real number, but remember, we started with the assumption we had a listing of all of the real numbers. So it's in that list. The sup of A is some x sub k. But the sup of A is less than or equal to the inf of B, meaning the sup of A is bigger than all of these AIs, but less than all of these BIs. So the sup of A belongs to all of these intervals. However, the sup of A is x sub k, and we previously argued that any particular term from our listing can't belong to any of the intervals whose index is smaller than this subscript. So whatever x sub k is, it can't belong to any of the AI, bi, where the I is less than or equal to k, totally contradicting that it belongs to all of them. Okay, what did we do? The set of real numbers is uncountable. The details of the proof we just did, honestly, not super important. It's not something we're going to repeat over and over again. What we will use again is a construction of these nested intervals where you have right endpoints and left endpoints that are kind of approaching each other while always being within the previous step. We will do that a couple of times. Intervals are just defined, and we gave the notation. One thing that is useful to note, it was a proposition that we didn't prove, it's left as an exercise. Intervals are exactly the sets that have this property that given any 2 points in the set, every single real number in between them is also in the set. Okay, if an interval contains more than 1 point, it is automatically uncountable.